In this video, we're going to look at the process of effusion. This is a form of diffusion, except for this is actually defined as the escape of a gas molecule through a tiny hole in a container and moving to the outside of that container, sometimes in a vacuum, and sometimes into other mixtures of gases. And essentially, you have all seen this process happen where you'll get a helium balloon for a birthday party, and then over time, what you'll see is the helium balloon will deflate and no longer float in the air. And this is because the process of effusion is actually occurring. There are actually tiny little holes in the helium balloon, and as time goes on, the molecules of helium are moving inside the container, and eventually what they'll do is they'll hit that hole and they'll escape the container or the balloon and be lost in our atmosphere. And over time, the balloon will deflate because there are less molecules of helium within inside it. One of the scientists that described this process was Thomas Graham, and he developed this thing that we now call the Graham's law of effusion. And he basically stated that the rate of effusion is indirectly proportional to the square root of what is considered the molar mass of that particular molecule of gas. And so most of the time, we don't technically calculate the rate of effusion alone. We usually compare it to the rates of effusions of other things. So when you're comparing rates of effusion, the way that you do this is you typically say, hey, the rate of effusion of gas A is to the rate of effusion of, say, gas B. And the way that we're calculating that, if you know what the actual official rate of effusion is, then you can divide these two, and that'll tell you a ratio of how much faster or slower, say, gas A is moving out of the container than gas B. There is, since the rate of effusion is indirectly proportional to the square root of the molar mass, there's another way to write that, saying that it is also, you can compare rates of two gases by taking 1 over the square root of the molar mass of A divided by 1 over the square root of the molar mass of B. Now, we don't really like having fractions with inside fractions. And so if you multiply, taking this numerator, the reciprocal of this, and multiply the numerator and denominator, and then you do the same thing with this guy on the bottom, the 1 over the square root of molar mass of B, multiplied by the reciprocal on the denominator and numerator, you get this equation here. And so if you'll notice, now the molar mass of B is on top, the molar mass of A is on bottom, but you no longer have fractions within a fraction. And so it is a way to compare rates between the gas effusion rates of A to B using this equation, or this here. And if you just don't mind having fractions in a fraction, you can do that as well. This is just the simplified version of this equation up here. So use this idea to try to help solve a problem. So here we say at a particular pressure and temperature, okay, we don't really need to know what that is, but it's just saying that, hey, here it is. Nitrogen gas effuses at a rate of 79 milliliters per second. Okay, so now we actually are given an effusion rate here. So not the molar mass, although we would know what the molar mass is because we have the formula. And then it says, using the same apparatus, and meaning how they calculated the rate in the container that the gases happen to be in, at the same temperature and pressure, so, okay, at what rate will sulfur dioxide effuse? Oh, okay, so we're going to have to use some version of these equations over here in order to solve for essentially what is considered our second gas. So a couple of things we need to note. What's sulfur dioxide's formula? SO2. We need to know its molar mass as well, 64.06 grams per mole. Might also be nice to know nitrogen N2's molar mass, 28.02 grams per mole. And essentially, this is what we're going to do. We're looking at the rate of nitrogen to SO2, all right? And so what we're going to do is go, hey, we to do that rate of N2 over the rate of SO2. Well, we know the rate of N2 is 79 milliliters per second. What is this rate here? Well, in order for us to figure out what this value happens to be, we don't have anything other than the formulas and their molar masses. So what this could actually set equal to is the square root of SO2 molar mass divided by the square root of N2's molar mass. And so if we can put these two in these equations, then we can solve for that as well. Okay, so let's try that. So we're going to do 79 milliliters per second over we don't know, and that's going to equal the square root of the molar mass of SO2, 64.06 grams per mole, divided by the square root of N2, which is 28.02 grams per mole. And when you do this math, this is kind of what it ends up looking like. It'll be 79 milliliters per second over X. And this math here, you can calculate this to be essentially, say, 1.5, right? The grams per mole will cancel out. And so to solve for X, essentially what you would do is take 79 and divide by 1.5, and this gives me a value of 53, and this would be 53 milliliters per second. So this is the rate of SO2. Okay, so this is how we use Graham's law to calculate things about rates of effusions. And again, you'll need to know molar masses more often than not will help you solve for those particular problems.